Okay, purpose of this video is show you guys how to do assignment 7. We are working on chapter 8, decision tree algorithms. And we have a set of loan data, which we have split up into sample values and non-sample values. So we're going to use the sample values to build a decision tree model, and then we're going to test that against our non-sample values. So first thing we need to do really is decide which one of our variables, our age categorization, our income categorization, or our credit risk categorization is sort of best predictive of this on-time variable that we have here. So we're trying to figure out, okay, how can we predict on-time loans based on these other variables? And the way we're going to do that is we're going to use entropy measure to gauge which one of these variables has the most discriminating power. And in the case of our calculation, we are going to basically look for the value that produces or the variable that produces the lowest entropy calculation here. So what I've done for you guys is I have the calculation for the age variable in here, and you'll need to fill in the risk and the income here on our first iteration. So if we take a look at the calculation, all we're doing is we're pulling the values from our loan raw sheet where our column L equals yes, and that's the column that determines whether or not we're using our sample data. Then we are looking for the column B values from loan raw, this loan raw sheet, that are equal to this A5 cell, which is where age is equal to young. So if we jump over to loan raw here quick, we see, hey, let me hit escape there. If we jump over to loan raw, we see that, hey, column L is whether or not we have a sample, so we're going to be pulling values that are equal to sample. And then column B is for our age categorization, column D is for our income categorization, and column column I is for our risk categorization. So let's just take a look here then. Here we're using column B, this corresponds with age, and we're counting using the count ifs formula, all the values for age is equal to young. Now we want to count the positive outcome and negative outcome values. In our case, a positive outcome is equal to an on-time payment. And so we just need to change our formula by adding one more criterion to our count ifs. And we're going to say, hey, count all instances of young where we had the positive outcome of on time. And then for the negative outcome, we are just going to count the opposite, where we do not have on time. So that gives us 8 positive outcomes, 4 negative outcomes. We can then take these formulas and just copy them down here at this point because they have relative cell references. We can copy paste them down through, and we will perform the same calculations for the middle age category and the old age category. So if we wanted to do the same for risk, we could just take this and change the column that we were referring to. So let's just go ahead and copy our formulas down to this risk. And now we know we want to change, instead of referring to the age category, we want to refer to the risk category. So if we jump back over here, we say, oh, risk was in column I. So instead of looking for column B, we're going to look at column I, which we just do by putting an I in there. And now we can see that we are counting all values where risk equals low for our data set. Then we just need to make the same correction here. for I. Oops, messed that up. Forgot to put the semicolon in there. And again, change our reference for I. All right, now that I've got this referring, the cell references correctly referring here, I can go ahead and just copy these down. And now we are pulling all the values for low, high, and medium for risk. All right, so then we have this formula given to us by the textbook where our value is equal to negative positive outcomes divided by total outcomes times the log base 2 of this same calculation times or minus the negative outcomes divided by the total outcomes times the log base 2 of that same calculation. And then we multiply it by the percent of the whole data set to come up with our entropy calculation. So you can see here that I've got these values in here. We're dividing the positive outcomes by the total outcomes. We are using the log function inside of Excel, and we are referring to our positive outcomes divided by total outcomes with a base of 2 to return the value that we would have to raise the number to or the exponent we'd have to apply to the number 2 to get the value of our positive outcomes divided by our total outcomes. Then you can see we're doing the same calculation here for negative outcomes. Again, doing the log calculation to get the exponent of 2 to produce our number. And then I'm merely doing the math in a couple of different steps here. So in the first step, we've just filled in the pieces of our formula. In the second step, we've completed the operations. So we have negative F5 times our log value minus our negative outcome calculation with its accompanying log. Then we subtract the second value, which happens to be a negative from a first, which is the equivalent of addition, and then we multiply it by the percent of the total that this represents. So if we see here, this is 0.6 is equal to the 12 values of young that are the total of the 20 sample values we have. So we just do the same thing for each of these down through, and that's how we come, and then we add all of those values together to get the entropy measure for the age variable. So now if we wanted to do the same thing for risk, because these are all relative cell values here, we should be able to just copy paste. So I'm going to copy paste those values. That gives us our entropy calculation for risk. And then I can do the same thing for income, understanding that I need to fill in my positive, negative, and total counts for my income categories. So to do that, we'll just copy our risk calculations on down here. We know we need to not refer to column I anymore. We need to refer to the income column. If we take a look at the lone raw, our income category column is D. So I can come back here to my calculations and we will refer to column D instead of column I. And I do that by just D:D. And I can do the same thing for the positive and negative outcome values here. So replacing I with D, replacing I with column D, And now that I have those, I can just copy paste these. And we've got the same calculations here for our income. So if we look at this, if you remember, the lowest value is the one that has the most discriminating value according to our textbook author. So here we can see that 0.446 is the lowest value here, which means that we want to do our first roll in our decision tree utilizing the risk variable. And we can see here that the low variable has a absolute reference that we can use. So we could say when risk is equal to low, we would expect our values to, or our folks to be on time, right? That'd be the first rule that we would apply. So if we come to our rule sheet, then we've got our sample data here in our rule sheet, and we're going to build out our decision tree rules here, one column at a time as we figure this out. So here you can see I've got the rule applied, and we are saying if our risk is equal to low, then we are predicting an on-time payment, and if it is not low, then we are predicting late. And then in this R1 correct column, we are just determining whether or not our rule correctly predicted the outcome based on our sample data. So the one little wrinkle we have here is we are treating default and late as equal. So all I've done here is said, hey, if our predicted value is equal to the actual value, then we have correctly predicted it, so we'll say yes. And if the two are not equal to each other, we just want to check whether we have a default value here. If basically just saying if either of them are late or default, those are equivalent, and we have correctly predicted, or lastly, we have not correctly predicted, right? So here, you could see that we have 5 values which were incorrectly predicted by our first rule, which I have summed those up down here using this count if, saying, hey, for every one of the values here, count the no's, the ones where our rule didn't work. And if we were to divide that number by the total number of values we have, 20 in this sample, we would have an expected error of 25%. Alternatively, we can use the probability to calculate our expected error here. So our rule says if our risk is equal to low, then we predict that our payment will be on time. So to calculate our expected error, we can look at what is the probability of not low, which is the total values not equal to low divided by all of our samples. And then for those values, what is the probability that they will be on time, i.e. the opposite of what we would predict for them. So there we could just say not equal to low, then our on time, column K equal to on time, and divide that by the total values that are not low to get a probability of 50%. We multiply those two values together and we get the same expected error, 25% that we predicted up here. Personally, I think this value is a little easier to calculate, but it's good to know both ways to go about this, even though they get you to the same place. So, all right, now we need to calculate rule 2. So then we will need to do a second entropy calculation. So for our second entropy calculation, we need to exclude the calculation we did in the first value where we said we will be using the low value of risk. So you can see right here, I am going to calculate the total count for where the age is equal to young, and then our risk is not equal to low down here. So to make our lives easy, we can just go back and grab our age calculation that we did on our first entropy calculation, and we can just alter it slightly. So I'll bring this over here, and we will paste this in. And really all we need to do is apply this this criteria to exclude the risk values equal to low from our positive and negative outcomes. So I'm just going to go ahead and copy that piece of this formula here. We will stick it into our positive, and I need a comma there, our positive outcome calculation and our negative outcome calculation. And then we could see that we are correctly splitting the total into positive and negative. Now that we have that figured out, we can just go ahead and copy paste these right in to our values, and then we can ensure down here that our check total shows the same thing, right? And then we get our entropy calculation. Now the only difference is now we're not going to use this percent total calculation as a part of our calculation, so we can just set that to 1 to give us our entropy calculation. So we want to check the same thing for income. So we know that we've correctly set these calculations up here, so we just copy paste them down. And we know the only thing we need to do is change and refer to our income category as opposed to our age categorization. So if you remember, if we just take a look at our loan raw sheet, our income category is in the D column. So if we jump back over here, we just need to not refer to the B and instead refer to the D column. So we will go ahead and change that to D. And we'll do the same for our positive and negative outcomes. And one more time. And now that we've got those correct, we can go ahead and just copy paste these down through. And then you can see that our total is adding up to 20 here because we don't have our total excluding the risk calculation like we do the rest of our calculations. So if we want to fix our check total, we can just come copy this out of here. And now we'll add it to our check total just to make sure we've got all this stuff correct, and then everything adds up. At this point then, we should be able to just copy paste the calculations, and we can grab these really from our other sheet or from right here. Either one ought to work just fine. I'm going to paste those in, and we can see now with these two calculations that the greater discriminating value, because the number is lower, is offered to us by where age, our age category, where risk is not equal to low. And then if we examine the values here, we have our middle giving us an absolute rule where we are essentially saying if risk is not equal to low and age is equal to middle, then we would predict a negative outcome. So we can go ahead and apply that as a rule now to our decision tree. So now we can pop back over here to our rules and fill in our second rule. So here you can see I've put this calculation together. I'm just going to copy this and paste it in here. And what we're saying is for this second rule iteration, if the risk category is equal to low, that means we would have already touched it with our first rule. We want to exclude it. But if not, we would like to say if our age category is equal to middle, we will predict a late outcome Otherwise, we will predict on time. And so now we can copy paste this all the way down through. And then we just need to check if our rule correctly predicted our predicted outcome here. So again, we're going to say if the first rule touched it, leave it alone. Otherwise, check and see if our predicted outcome is the same as the actual outcome. So now I should be able to paste that into here. And we will copy paste that down through. And then for the sake of convenience, we'll just change the formatting here so it's a little easier to see what's going on. So I'm just going to use the conditional format. I'm going to use a highlight, and then I'm going to say if our value is equal to no, we'll just take this default light red fill. And then also to further make this easier for us to read, we will apply one more conditional format, and we will say if our value is equal to exclude, then let's go ahead and format this thing with a gray background. We'll just pick that out, say OK, and OK. And now we can see sort of if visually if we're kind of getting better with each iteration of our rules here. So we can see in our first rule we had 5 incorrectly predicted values, and in our second rule we had 4. Naturally, you would say, hey, that sounds better to me. You can see our expected error is predicted as 20% using the easy calculation. And then if we want to use the probability approach, we can go ahead and just modify our first formula. We'll paste that in here, and we can say, hey, if it is not equal to low, if our risk is not equal to low, and our age category is not equal to middle, so we'll just highlight our B values and say not equal to middle. So there we're calculating the probability of that occurring, and obviously I checked something up there. What did I do wrong? Oh, it's watch out for this. I had a count if formula in there. When you're using multiple criteria and you want to use count ifs, that's the one that tells us we have multiple criteria. So that calculates the probability of our rule, essentially, or of the antithesis of our rule, not equal to risk low and not equal to age middle. And then we need to calculate the probability of not being on time for that, because we would be predicting on time. So let's go ahead and calculate that. So really to do that, we just need to copy this piece of the formula from up here. We can add in the additional criteria of not on time. And then in order for this number to be correct, it has to be within the context of the first probability, which means we just need to divide it here. And then we can see that these two probabilities multiplied by each other give us that same 20% value, right? So our second rule is producing a lower expected error than just the application of our first rule, so that's a good thing. So now we want to go on and see about predicting a third rule. So here we really just have our income value left, and we can again just go steal our calculations from the sheet before. So we'll just go ahead and grab the income values here, and we will paste them in And then the only thing that we need to do is make sure that we are modifying for both the excluding our first rule and excluding our second rule. So we are excluding our second rule with this criterion here. So I'm just going to go ahead and copy that, and we will paste that into our other calculations to make sure we are doing them correctly. We will do the same down here. And then finally, we will correct our positive and negative calculation here. And then if we want to make sure that our check total is correct, then we can calculate. We can take both of these calculations. And there we go. So now we're just looking for which one of our income values has the greatest discriminating value. And here we could see that the high has the lowest number of 0. And then we have our same criterion happening again where we have an absolute value. So we're saying for our third rule, if income is equal to high, well, let me say that again. If risk is not equal to low and age is not equal to middle and income is not equal to high, then we would predict the negative outcome of not having an on-time. So now we can go ahead and put that rule in as well. So here you can see I've got that rule created. So I'm just going to copy that and we'll paste it into our Rule 3 column. And you can see that we are using here this OR operator, and we are saying, hey, you know, if our the essence of this is to say, if our first two rules have not been applied, then if income is equal to high, then we will predict a late outcome. Otherwise, we'll predict on time. So again, we will drag this down through, and it will exclude the calculations from our first two rules. Then we can just check to see if our rule has correctly predicted the outcome. We'll go ahead and put that in our R3 correct column. And again, we will pull this down through. And here you could see that we have incorrectly predicted 3 values this time around, giving us an expected error of 15%, which is obviously better than the 20% we got with the application of the first two rules. If we wanted to calculate this utilizing the probability approach, we can just copy paste our last calculation, and we can add in that income is not equal to high here. So we'll just highlight that, and then not equal to high. And the second part of our calculation we can get by just copying the first part. And then we're also saying we would predict on time, so what our error will be represented by when it is not on time. So again, we just add this in, not equal to on time. And then we have to divide that by the occurrence. and we get a predicted value of 15%. So now what we could do at this point is we could actually use the remaining values of income to see if we can get any sort of additional lift from them, or any if we can reduce our error. We would have to add the probabilities of the two cases we have left here, because if we take a look, we can see that neither one of these rules produces an absolute outcome, but the sort of the greater discriminating rule here is average, basically saying that if average, we would predict that we would get a positive income. If we come back and apply that rule and go ahead and drag that down through, we have a formula for determining how correct we were. Oops. We have a formula for determining how correct we were. And we can see that it doesn't improve our outcome. I'll leave it to you guys to fill in these pieces here, understanding that you're going to add up these two probabilities. But for either one of these, the gist of what we're going to discover is that neither one of the rules that we might be able to produce off of these other values of income is going to improve our expected error. And so therefore, there is no reason in including these in our decision tree. So just to prove that out, we put these last values in here. You can see where the value, or the predicted value of our rules, doesn't improve with either of these cases. So then the last thing we just need to do is check this against our non-training data set. So I'm just going to go ahead at this point. It's pretty easy. I'm going to copy our rule 1 through 3 values. I'm going to jump back to our lone raw sheet here. I'm going to turn this filter off so that we get all of our values. I'm going to turn this filter off so we get all of our values. Then I'm just going to paste that formula in here. It'll have the same relative cell references. And I'm just going to pull this all the way down through. And that way we can apply it to both our sample and non-sample data. And then up here you can see that I've got our training and non-training results. If we take a look, our training should correspond with what we just saw on the rules sheet, and it does. And then we can see how well this model performed against our non-training data. So we can see on training, we had an expected error of 25%, on non-training 44%. The second rule did significantly better on the non-training data set than the training, and then we got a very marginal increase from the third rule. So that gives us a sense of how well our model that we built is performing against our non-training data. So that will get you all the way through assignment 7. If you just get to this point and save this sheet, you can then upload that to the assignment and you will have completed this. And then in assignment 8, we're going to take the same data set and perform these same operations inside of R. All right, hopefully that'll get you guys through assignment 7. If you need any help, reach out to me on Skype and I will be happy to help you.